Okay, in this segment we're going to be looking at the effect of base currents on translinear circuits. So we're going to start out by looking at our one of our example translinear circuits that we looked at. This is going to be the squaring reciprocal circuit. If you recall, our simple analysis basically said, well, this is Ix, this is Iy, and this is Iz. Translinear principle implied that Ix times Iy is equal to Iz squared. Which means that Iz is the square root of Ix Iy. Now, writing this kind of equation where Ix is equal to the current flowing in this collector hinges on the current, no current going this way, right? No base current. But if we were to ignore the base current flowing into this output device here, the base current that's flowing into the second transistor, this Iy transistor, is at least going to be Iy over beta. That's terrible. So the current flowing this way is at least Iy over beta. It's there. I should say just greater than. And so if we have a finite base current assumption, then in order to say that this current is actually Ix, we say Q1, in order for Q1 to have Ix as its collector current, Ix must be much greater than Iy over beta. In order for us to be able to neglect the base current being taken by Q2, this must be true. It's actually going to be the sum of whatever Iz over beta plus Iy over beta is. And you can imagine very easily a situation where, for instance, in the lab, you're going to be setting Iy to some level. We can set Iy completely independently of the level of Ix, right? Ix and Iy are completely independent. Inputs. And that's unlike the current mirror. For instance, in the simple current mirror case, there was a definite relationship between the input transistor's base current and the output transistor's base current because the two transistors were making the same current, or there's a fixed ratio between them in general. In this case, we have constraints that are required on two independent inputs. Okay? And so you can very easily set, let's say IY to, let's say 100 microamps, and make IX equal to 10 nanoamps. Right? These numbers are not outlandish. We've been sweeping our transistor currents or collector currents over a wider range than this. If beta is 100, then the current in here is about 1 microamp. The base current required by Q2 is 1 microamp. And if that's the case, then none of this current will go into the collector current of Q1. It's all got to go into satisfying the base current of Q2, and then it's not even going to be enough. So we have some real problems here if constraints like this are not met. Okay, we might be able to go in and think about, assuming the ideal analysis and saying that this is IZ and saying that IZ over beta is the current flowing into the base of this transistor and refine this kind of inequality. But you kind of get the sense of what's going on here. These base currents can very easily be non-negligible in these kinds of circuits where we have different branches with independent currents flowing in them by design. And so what you'll see, for instance, this is this same circuit here, and some measured data taken from this circuit built on a breadboard out of 4 transistors on a MAT14 transistor array. And this is a similar kind of experiment to what you'll be doing in Lab 4, where you're going to sweep one input for at least 3 different values of the other input. And these black lines here represent the ideal square root of the product of IY and IX at each point. So the log log scale here basically turns these kind of power law, product of power law relationships into straight lines, which is a very nice way of looking at the behavior of these circuits over a wide range of inputs and outputs. And you can see that there is a range of currents where the circuit very nicely follows, modulo some slight systematic offsets, which are probably due to the early effect, the behavior that we predict with our 0th order analysis. But you can see that at lower values of IX, we have this kind of place where all things start breaking, and now we're down by a factor of 100 here. So we're following a similar slope maybe, but now instead of being up here, we're down here. This is the 100 microamp case, and so this represents the base current of the IY transistor being the largest, and so there's kind of a minimum threshold below which IX has to fall. Maybe it's a microamp to be conservative here, but you kind of get the sense that it kind of snaps into place once IX gets above that threshold, and you, lo and behold, 100 microamps divided by 100 is about 1 microamp. Okay, and if we go down to 10 microamps on IY, you'll notice that this place shifts down by like an order of magnitude. And you'll also notice that for the 1 microamp case, we're not even really seeing this. It's off the plot here on the left-hand side. So this is due to the base current of the second transistor, what's going on down here. Now there's something else going on up here, where you can start to see some deviation on the high end. And again, you can start to see, you can't really see it in the 100 microamp case, but you can start to see it here for the 10 microamp case, and you can start to see it much earlier, about an order of magnitude earlier, for the 1 microamp case. So there's sort of a window around IY here where you get a good range, but the range slides up with IY. and it probably is like a factor of beta down and a factor of beta up or something like that. But it varies by circuit, and it's something that requires some thought to identify precisely what's going on at the two ends. If you take the same circuit and you flip things around, you'll see a similar kind of effect, but it's a different. It manifests itself in a different way. But you still see this same sliding down or sliding up of the window over which the behavior is following what you expect from the ideal translinear circuit analysis. Okay? So that's kind of just what kinds of things can happen with finite beta effects. And so now I want to spend a little time thinking about, well, what can we do about that? What can we do about finite beta effects? How to mitigate them? Well, the answer is have something else supply the base current. Right? That's the same similar kind of situation to what we said for the current mirror. And so one solution for this geometric mean circuit, which obviously you can't see because I haven't flipped the slides back over. So for the geometric mean circuit, one thing we could do is we could buffer into the base and notice we also have to buffer in the base of this transistor. And it's not quite where I'd like to have it. Right, so this op amp is going to supply the base current for and this one is going to supply the IX over beta. And this could work. You could also possibly use a beta helper type arrangement where you have a sort of an emitter follower instead of a full-on op amp, or maybe a simple op amp like we'll be talking about in a few weeks. Maybe made with 5 transistors or something instead of 24 or so. But this kind of arrangement could work. However, it's not the best kind of thing we could do. And to illustrate that, I think what I'd like to do is I'd like to use the other circuit that we've been considering. So this is an example of using op amp buffers to supply the base current. So this we're going to illustrate on the squaring reciprocal circuit. So this better arrangement still makes use of op amps, but it has some advantages that we'll discuss here. So the prototype circuit, or the simplified sort of prototype circuit, is this one. we have a stack of two diode connected transistors. We have something like our emitter follower. And then we have our IZ. And the translinear principle, just to review here, this was IX, and IY. The product of these two currents is equal to the product of these two currents, so IX squared equals IYIZ. IZ equals IX squared over IY. But again, here we have a situation where we can have IX and IY. They're independent input currents, so we could set IY, let's say, at our 100 microamps, and IX, if that's 1 or 10 nanoamps, we're going to run into problems with the base current of this device. Okay? So we still have to have IX much larger than IY over beta. What if we take that same loop of transistors? Okay, what does that loop look like? So that loop of transistors looks like this. And I'm still going to diode connect this one. This is IZ, IY, so we want to have this sort of arrangement. So this is the same loop of transistors with the same collector currents flowing. But what we're going to do is we're going to change the arrangement by which we get the collector current of this transistor to be IX, the collector current of this transistor to be IY, and then this transistor sees what its base voltage is, and what its emitter voltage is, and it produces IZ according to this translinear loop equation. Okay, what we're going to do here is we're going to connect the bases of these transistors to ground. And we're going to assume our op amps run on a split supply. For example, maybe plus or minus 2.5 volts with ground in the middle. So the idea here is they can drive below ground. If that bothers you, we can move this point up to 2 or 2.5 volts and run everything on a 0 to 5 volt power supply. That would be entirely equivalent. Okay? But what we're going to do is we're going to force a current, IX, into the collector of this transistor, just like before. Only now what we're going to do is we're going to take an op amp, like so, plus and minus, and the plus input is going to be connected to the base, which is ground, and the minus input is going to be connected to the collector, and the output is going to drive the emitters of these two transistors, the diode connected transistor on the bottom of the stack and also the output transistor. So let's think about how this works. So the op amp, first of all, the question is the op amp's feedback negative? Well, we're feeding back to the inverting input, so the output goes through the stack of two transistors and it comes back to the inverting input. So if the effect of moving this voltage causes this voltage to move in the same direction, then the gain of this two transistor stage is positive, and we would have negative feedback. Okay? So the way to check this qualitatively is to think our way around this feedback loop. So let's suppose, for the sake of argument, that this input current is a little bit larger than the collector current. Okay? So if this current is too big, let's call this Ix prime. So suppose Ix exceeds Ix prime, right? So that means that we have a situation where KCL is not satisfied statically by these currents. And so the excess current Ix minus Ix prime goes into the node capacitance. So remember, there's always some implicit capacitance here. And that causes this voltage here, we can call this Vx. So we have plus dVx dt. That means that Vx is going to increase. Well, Vx let's call this VE for V emitter. Vx increasing means, since that's the inverting input, means that VE is going to go down. Okay, so the op amp is going to drive the output voltage, its output voltage, lower. Well, what effect is that going to have on this current Ix prime? Well, this is a bipolar transistor. So what happens when I make VE go down? Well, if I make VE go down, that increases the current by increasing the base emitter voltage here. If I decrease the emitter voltage without changing the base voltage, Ix prime is going to increase. And that's going to reduce the difference. Okay? That's going to mean that we're turning up the current level in this branch to meet the new value of Ix, or the larger value of Ix. That means that less current's going to go into this node capacitance, and Vx will stop, which is the thing that's causing these changes, when Ix is equal to Ix prime. Okay? So it is a negative feedback arrangement that will drive this voltage to be whatever it needs to be so that these two currents are balanced. Well, the op amp is also attempting to make its input voltage difference equal to 0, which means that Vx in equilibrium is going to basically be ground. Or the op amp tries to drive its input difference to 0. Right, so we're going to have a situation here where at equilibrium Vx is going to be equal to 0 volts, and the current flowing through here is just going to match the current that we're forcing in. And so this transistor here is not diode connected directly like this, like it is here, but it is, you might say it's virtually diode connected, because here the collector is at the same potential, is actively being held at the same potential as the base. So VCB is equal to 0, but it's not actually physically diode connected. Okay? So now we're going to actually do a very similar thing with the IY transistor. So we're going to have a second op amp over here. We're going to force IY now into the collector instead of pulling it out of the emitter. And we're going to drive this unconstrained, heretofore unconstrained base slash emitter node. Well, here Vy is going to be at equilibrium 0 volts, and the collector currents are going to be equal. So, and you can chase the cause and effect around the feedback loop here and convince yourself that the plus and minus inputs here are in the right sense. I mean, it's basically the same type of arrangement without this extra diode in the way. But this is interesting because over here, okay, we pulled a current out of the emitter, and we were relying on the fact that beta is very large so that alpha is nearly 1 to make the collector current equal to the emitter current. And also we were neglecting the base current flowing here into the output device. Well, here we're not supplying any base currents. We're not having any base currents being stolen from our KCL equations here at the collectors of our two input devices. We're forcing the collector current here directly. So it's not alpha times the current that we're putting in is what the collector current is. It's actually the collector current. If these op amps really draw no input current, like they should, and if they're made with CMOS devices, that's to a very good approximation true. The input bias current could very easily be in the picoamp range. With CMOS op amps, as we'll talk about starting in about a week or so. So the KCL arrangement here at the input nodes is very, very accurate. And the other thing is to note here, VCC is the voltage on the collector of the IY transistor. And that means that it has potentially a very large voltage across it, right? So if this voltage here is the emitter, we basically have one diode drop up, or one VBE up from ground, which might be put this node at about 0.6 or 0.7 volts, whereas VCC might be up at 5 volts. So this device has like roughly 4 volts and change across it, which means that it's going to be biased way up in its collector characteristic, whereas all of these devices, these two devices, have about 0.6 or 0.7 volts across them because they're diode connected. So they're down very low on their collector characteristic. And so because this transistor is biased up high on its collector characteristic, we can expect some systematic gain error or transfer error due to that mismatch in the VCEs of all these transistors. But what about this device? This device is now virtually diode connected, just like this device is. The base is at ground, the collector is being held at ground. And so the VCB of this transistor is 0, just like it is here for this actual diode connected transistor. So all three of these devices are being held at comparable collector base voltages. I'm sorry, collector emitter voltages, which means that they're going to be at a very similar point on their collector characteristics, and we're going to have much less systematic transfer error due to the early effect. So this arrangement, in this arrangement, we're not supplying any base currents. There are no base currents stealing current from the input KCL equations. And we're holding the collector to emitter voltages of all of the input transistors to be comparable. And so for a given output voltage, this arrangement is going to have much less systematic error due to the early effect than this sort of arrangement would. Okay. The other neat thing about this, and you'll see this in the post lab, is that we can actually do current to voltage conversion here. So we can basically replace these current sources with some resistor driven by a voltage. And if we've taken this point to be ground, well then, what's the current flowing through here? Well, it's just Vx minus 0 over R. And Iy is Vy minus 0 over R. So by maintaining this node fixed at ground, we get the ability through just a single resistor at the front end to linearly convert our input voltage into a current if we need to do that. Okay, that's not necessary, but it's a nice bonus of this arrangement. So anyway, that's going to be it for this. Like I said, if we wanted to have our op amps be single-ended, we can simply just raise this point, the base node here, up to a voltage that is sufficient to allow the maximum voltage difference we expect between the base here and the emitter, which is basically maybe 1.6 volts at most, to be allowed. So we might put this at 2 volts, let's say. So if we move this up to 2 volts above ground, and our op amps are rail-to-rail op amps that can drive down near the ground rail, then we are in business. Anyway, so that's it for this. We'll see you next time.